wanted to know the volume of this cylinder with a given radius and height, then I remember from my geometry class that that volume is pi r squared h. And basically the idea is it's the area of the base, which is pi r squared because it's a circle, times the height. Now, this is true simply because the radius remains constant throughout the entire cylinder. What if we have an object, though, where the radius varied? Like this. Okay, now we've got pi r squared here, but if I move like a millimeter to the right, my radius has changed. And it's getting smaller and smaller, and then it gets bigger and bigger, and then smaller and smaller. So how are we going to find the volume for this puppy? We need calculus! Yes, we need calculus. All right, so let's start with a simpler example and work our way up to something like this. Let's say that our radius follows the function y equals the square root of x. So basically, then we're going to take this function and we're going to rotate it around the x-axis. And it's going to look something like this. Bam! There we are. So now, notice we've created a three-dimensional object because our curve is rotating around the x-axis. Now, notice the radius in here is small, but it gets bigger and bigger and bigger, and it gets bigger by the function y equals the square root of x. Now, here's the situation. We're going to look at this volume as a whole bunch of cylinders. And we're basically a whole bunch, I mean infinitely many. Now remember, we calculate the area of this thing by infinitely many rectangles. Well, now we're doing infinitely many cylinders, which is going to get us the volume. So what's that going to look like? Well, each one of those cylinders will start here and work our way to the right. And notice then as we go, the radius gets larger and larger, but there are infinitely many of these cylinders. So we're integrating from A to B of the function as our radius. So it's pi times the function squared times the dx, which is the height of each cylinder. Okay, so let's actually see how this works mathematically. So, let's see. Yeah, we'll just quit this. All right. Now, yeah. Notice on page 446, we've got the curve y equals square root of x from 0 to 1. Now, I'm going to hand draw this because that's what I want to see on your paper. So we start with our graph, and let's just make 0 to 1 right here, and 0 to 1 right there. That's the 0 to 1. Now my function is going to be the square root of x, so it's going to be the square root of 1 is 1, and my function looks like this. Now if I rotate that around the x-axis, then it's going to have a mirror image on the bottom side, and then when I rotate, it ends up looking like this. Yeah, let's just make, yeah. We'll just make it like that so it's opening this direction. Okay, so there's our object. Now, the volume of this equals pi r squared h. Now, first of all, pi is a constant, so we're going to keep it outside. Now, each cylinder is going to be dxy. Now, what's the height of the cylinder? Well, it's going to be the radius at any point along here. So that radius is going to change as we go. So it's pi r squared. Now r becomes the function because at any point here the function is my radius. So it's pi r squared h. See, we've got the pi r squared, radius is the function, which is square root of x, and the height or the thickness of each cylinder is going to be dx between 0 and 1. Okay, so now this is a piece of cake because the square root of x squared is just x. So this equals x squared over 2 from 0 to 1, which equals 1/2 pi. So that would be 1/2 pi cubic units. Now, the key thing to realize now is it's just like we were getting area, only we're getting volume now, so it's pi r squared h, but the r is going to be the function. And so you just plug it in here. The most difficult thing of these types of problems is setting it up. Once you have it set up, the integration is really easy. Okay, so let's do another one. So this time, we're going to rotate around the y-axis. So we're going to start with y equals x cubed and y equals 8. Okay, so y equals x cubed and y equals 8. And so we're revolving around the y-axis this time. All right, well, let's graph that. So I've got okay, my function y equals x cubed, so 1 cubed is 1, 2 cubed is 8. And we've got the y equals 8, which is the horizontal line at y equals 8. We're going to take this shape now and we're going to revolve it around the y-axis. So we've got the mirror image on this side, and we're rotating it like that. So, the volume, once again, is still pi r squared h, but notice the r is now horizontal, and the h is vertical. So in other words, we've got the h's, each each thickness is going up the y-axis. So what we have here is volume is going to equal pi times the integral from, now notice, we're not going from 0 to 2. We're not, remember our thickness is a dy. So we have to go from y equals 0 to y equals 8. Of, now what we do is we say top minus bottom. Top minus bottom. So the top function is y equals 8. And the bottom function is y equals x cubed. Cut, take 2. Okay, we're going from y equals 0 to y equals 8. So what we need is the function of y. So what we do is we say, all right, y equals x squared, or x cubed, and I need x as a function of y. So this means I've got x equals the cube root of y. Now, so I'm going from x equals the cube root of y, or I'm sorry, I'm going from 8 down to the cube root of y. So we're doing the integral from 0 to 8 of, oh no, it's in black, how embarrassing, of the cube root of y dy. Oh, squared. All right, here we are. So it's pi r squared times h. Now, we're going from 0 up to 8, and remember, since our disks are horizontal, they're dy thick, and that means we have to have our function in terms of y. So we had to change it from y as a function of x to x as a function of y. And we still have pi r squared h. So now, once again, an easy integration. So we just say this equals pi times the integral from 0 to 8 of y to the 2/3 dy. Then when I do the integration, it becomes y to the 2/3 plus 1 is 5/3 over 5/3 from 0 to 8. So this equals 3/5 y, rats. 3/5 pi times y to the 5/3 from 0 to 8. All right, now 0 is going to make it 0, so that's nice. So we put in an 8 here, and we have the cube root of 8 is 2. 2 to the 5th is 32. So now we have 32 times 3, which is 96. So volume is going to equal 96 pi over 5. That's it, game over. Okay, now we've done one example where our axis of rotation is horizontal, and that means we have to have dx thickness on each disk. That means we have to have the y as a function of x, because we have to match the dx. Now, the next example we did, we've got horizontal disks, which means they're dy thick. that means we have to have our function in terms of y in order to do that. So we had to go from y equals x cubed to x equals cube root of y. Now, we're about to do a new situation that's called washers. And this is where we have two different functions involved. So let's take a look at that on our trusty calculus in motion. Let's see. All right. All right. We have our first function that's going to be y equals x. What's wrong with this? Okay, so y equals x, and we've our second function is y equals x squared. Okay, and we want our a to be at 0. There's our axis of rotation, and we want our b to be at 1. All right, now, when we rotate this, that doesn't really show it very well. Yeah, that's too small. Okay, let me just draw it for you. All right, so what we have is y equals x and y equals x squared. Now notice they're going to meet at 1, 1. So here's my y equals x, and here's my y equals x squared. And notice they both meet at 1, 1. Now, I'm going to rotate this about the x-axis. So that gives me basically a mirror image of what I just drew. And here's my rotation. Okay, so I have this shape that's being rotated around here. Now, if I look at one single disk, So notice what's happening here with one single disk. I've got a washer, or like a donut. Now, take a look at our donut if we look at it straight on. So here is that donut that we just drew. And that should be concentric. All right, now, if I want the area, remember, volume is going to be the area of the base times the height. And the height is dx. Well, what's the area of the base? Well, we have an inner radius that we'll call small r, and we have an outer radius that we'll call capital R. Now, the area here is going to equal the area of the entire thing minus the area of the whole. In other words, it's like the donut. You measure the entire donut, and then you measure the whole, and you subtract out the whole. So what we can do here then is factor out the pi, and we end up with capital R squared minus small r squared. So the area of this donut, or the area of this washer, is pi times capital R squared minus small r squared. Okay, now let's apply this to what we just did here. So we've got the area equals the integral, pi times integral. And you could put pi inside the integration too, it doesn't matter, it's a constant. And we're integrating from 0 to 1, from x equals 0 to x equals 1. And each thickness of each washer is dx. Now, what's capital R? Well, it's the distance from the x-axis up to the top function. And what is that top function? It's y equals x. And what's the bottom function? Y equals x squared. So the capital R is y equals x. So capital R squared minus small r, which is x squared, and we're squaring that. And then we have the thickness of each washer. So it's pi capital R squared minus small r squared times the thickness. That's it. Now, like I said, I put area. With the integration, it's no longer area, it's volume. Now, like I said, the most difficult thing is to set it up. Now that we have it set up, really easy integration. So we've got pi times integral from 0 to 1 of x squared minus x to the 4th dx. And that means we go pi times the integral x cubed over 3 minus x to the 5th over 5 from 0 to 1. That means we've got pi times 1/3 minus 1/5. And the 0 will make zeros. So 1/3 minus 1/5 is going to be 3, rats, blew a tire, 5/15 minus 3/15. So our final answer is 2 pi over 15 cubic units. Bam, that's it. All right, so this is the washer method, and it basically is called the washer method because we've got more than one function, and so we're not just measuring the volumes of each disk, we're measuring the volumes of each washer. Okay, now, another example where you're going to see washers is if the axis of rotation is something other than the x or the y axis. So let's take a look at example 5. Oh yeah, that's going to be lovely. Okay, so we've got the volume of the solid obtained by rotating the region that we just had about the line y equals 2. All right, so now notice every single problem that I'm doing, I'm drawing the picture. I want to see your pictures on every single homework problem. So we've got, and what are we rotating around? We're rotating around y equals 2. Okay, so better make this a little bit. Okay, so here's x equal 1. So then there's y equals 1. Oh, made it too big. X equals 1, x equals 2. That's too big. Okay. Ah, get the scale right. Okay. Okay. All right. Here's our original graph. We've got y equals x and y equals x squared. That's our original graph. Now, instead of rotating this around the x-axis, we're rotating this around the line y equals 2. So here is my new axis of rotation. So, the new, see, this is going to rotate up around here. So my new shape then starts out, I'm going to be going from 2 down to 2 up. And then I'm going to be going from 1 down to 1 up. And notice the inside is the linear function and the outside is the curved function. Now, what's my rotation look like? It's going to go like that. And like that. So there's the function that we have around this axis. Now, the volume equals pi times capital R squared minus small r squared times h. So that equals pi times the integral. Now, notice r washers dx thick or dy thick? Notice each washer is going to be a dx thickness. So that means my h will be dx. That means my limits of integration will be x values and my functions will be in terms of x. So I'm integrating from x equals 0 to x equals 1 of capital R squared. Now, what's my capital R? It's the distance from the axis of rotation to my bottom value. So what is that distance? Well, if we're talking vertical distance, then you always go top minus bottom. So that vertical distance is going to be 2 minus x squared. Y equals 2 minus y equals x squared. It's a y value minus a y value. Top y minus bottom y. So that's going to be minus x squared, and that's my capital R, so I square it. Now, I want my small r, so that's going to be the distance from the axis of rotation to the inner rotation, the inner function. And so my small r is going to be 2 minus x squared dx. Bam, that's it, game over. We have it all set up. Pi times the integral from 0 to 1 of capital R squared minus small r squared times the thickness. And remember, vertical distance goes high minus low. So now when we do this integration, just want to make sure we get that. Yeah, we actually have the same things in the book. So what we're going to do then is just distribute this out. So I've got pi times the integral from 0 to 1. Now, a minus b quantity squared. You may be discovering at this point why I drilled this into your brains in Algebra 2. Because now you need to be able to do it, and you need to be able to do it correctly. So we've got a squared minus 2ab plus b squared. Then we've got minus, once again, a squared minus 2ab plus b squared. Okay, now we just combine like terms. So I've got pi times the integral from 0 to 1. Now let's go, we've got 4 minus 4, so they're gone. I've got let's just start with the x to the 4th. So I've got a 1x to the 4th, and that's it. Then no x cubed, the x squared is negative 4 minus 1, which is going to be a minus 5x squared. And then the x's are going to be minus a minus 4, which is going to be plus 4x. And like I said, the numbers are going to be 4 minus 4 is 0. Okay, time for our integration. So this becomes x to the 5th over 5 minus 5x cubed over 3 plus 4x squared over 2 from 0 to 1, and that 0 is really handy. So now I just plug in my 1's and I get pi times 1/5 minus 5/3 plus 2. So if we turn this into 15ths, we've got pi times 3/15 minus 25/15 plus 30/15. So 30 minus 25 is 5, plus another 3 is 8. So our volume equals 8 pi over 15. Bam! That's it. Game over. Okay. So notice, drawing your function is going to give you a lot better understanding of your capital R, your small r, your dx's. Now, I want to do one more of these. Yeah, this is what I want to do. Example 6. All right, we're going to take this same function and we're going to rotate it about the line x equals -1. So x equals -1. Nope, didn't give it enough. You got to think about how wide the rotation is going to be before you do your axes. Okay, so here's my function. Here's x equals 1. Here's my axis of rotation at -1. And so it's going to rotate around this point. And so notice it's got to go from 2 away to 2 on the other side. Actually, have to put another x value in here. Okay, now, here's my function. Y equals x. Went a little too far there. And y equals y equals x squared. And we're rotating this around x equals -1. So that means this point gets rotated to here. This point gets rotated up to here. So there's my y equals x function, and there's my y equals x squared function. And here is my axis of rotation. Okay, so we're trying to get this, really what we're getting is not the volume of the bowl, but the amount of plastic that we're going to have to use to construct the bowl. Because it's the thickness of this bowl all the way around that we're interested in, the volume of that shape. Now, once again, we've got washers. And this time, though, our axis of rotation is vertical, which means which direction is it going to be, dx thick or dy thick? See, each washer here is going to be thickness in the up and down, so it's going to be dy thick. That means I need my function to be in terms of y, because if the thickness is in terms of y, the function needs to be in terms of y, and the limits of integration needs to be in terms of y. So, my volume here, well, before we do that, let's go back here and say this is y equals x squared. Well, that's y as a function of x. I need x as a function of y. I need my variables to be in terms of y. So what I do is I change that to, instead of y equals x squared, I solve for x and I get x equals the square root of y. So now, that's what we have here for this function, is x equals the square root of y. Now what about this function? Well, this one is y equals x. So if I want to move that and get x by itself, then x equals y. So I'm going then from, well, okay, I'm integrating from 0 to 1, but it's y equals 0 to y equals 1 this time. So the volume is still going to be pi times capital R squared minus small r squared times h. So it's still going to be pi times the integral. But this time it's from y to y, which is 0 to 1. Now, what is my capital R here? My capital R is now a horizontal distance from axis of rotation to the outer portion that I'm rotating. So this means, what is this distance? Well, if I want a horizontal distance, I go right minus left. If I want a vertical distance, I go top minus bottom. Now, if I go left minus right, I end up with a negative. So I go right minus left, which is x equals something on the right minus x equals something on the left. So that means it's, oh no, it's in red, how embarrassing. The square root of y minus the negative 1. Right minus left squared. That's my capital R squared. Now my small r goes from the axis of rotation to the inner part of the rotation, which is the x equals y. So this becomes minus small r squared, which is y minus negative 1. Quite squared. And this whole thing is times the thickness of each washer, which is dy thick. There we are again. Bam! All done. So let's do this thing. So y equals pi times integral 0 to 1. Now let's just clean this up. Y minus negative y, or square root of y minus negative 1 is just going to be square root of y plus 1 squared minus y plus 1 squared dy. Okay, so we're going to go pi times the integral 0 to 1, distribute this thing, so it's a squared plus 2ab plus b squared minus a squared plus 2ab plus b squared. Okay, so this equals pi times integral 0 to 1 of, let's see, so we have a negative y squared. We've got y minus 2y is minus a y. Then we've got 2 square root of y. Let's make this, instead of 2 square root of y, let's make it 2y to the 1/2. And then we've got 1 minus 1, which is 0. So that's it. Time for the integration. So I go pi times, now, negative y cubed over 3 minus y squared over 2 plus, now this is going to be 2y to the 3/2 over 3/2. So dividing by 3/2, same thing as multiplying by 2/3. So 2 times 2/3 is 4/3 y to the 3/2. Oops. from 0 to 1. Okay, now we plug in ones. So we end up with pi times negative 1/3 minus a half plus 4/3. And let's see, so that's going to be pi times negative 2, 6 minus 3, 6 plus 8, 6. So 8 minus 5 is 3. Is that right? Let's see. 6 minus 3 is 3. Yeah, that's it. So it's 3, 6, or pi over 2. So the volume of this thing equals pi over 2 cubic units. And yeah, that's always happy when it's the same thing the book gets. All right, so like I said, the toughest part of this